Let's get infrared and ultraviolet visible spectroscopy under our belts today. All right. In chapter 15, we covered. We're starting to learn various techniques that we use to elucidate the structure of molecules. We've learned how to name them, and we've learned different ways of representing them, different what we call projections. Some more useful than the others, depending on what type of information we're trying to gain from them. But the question arises, how did we get to that point? How do we know that these structures are there? And I think I mentioned last time we met that it used to be that if you wanted to prove the structure of a molecule, you had to synthesize it with various techniques that were guaranteed to give you certain types of functional groups, carbon chains, double bonds, triple bonds, whatever the case may be. And you had to prove that by that synthesis pathway that you ended up with the same molecule that you were claiming to have identified. And it was very, very tedious, obviously. But now we have various, well, I should say, the methods that we're investigating now are non-invasive. By the way, they don't destroy the molecules. They just probe the molecules to determine things about the molecules. I should qualify that. Last week, mass spectroscopy does destroy the molecule, right? But the methods we're going to start with today are non-invasive. That is, they don't destroy the molecule. Not intentionally, so to speak. So, we're going to look at several types of spectroscopy. There are a number of different techniques that have been developed. We're going to focus on just three. Today, we're going to look at infrared spectroscopy, ultraviolet and visible spectroscopy. And then in chapter 17, we'll look at nuclear magnetic resonance. These all involve bombarding the sample with certain types of electromagnetic radiation. Let's see. And then once we've identified the principles behind the technique, we want to use information that's gained from the technique to deduce structural characteristics of the molecules, because we know that we can write a molecular formula for a molecule, and it could be one of a dozen different isomers, structural isomers. All right, this is just an outline. We're going to spend a lot of time on infrared because it's extremely useful technique. Ultraviolet and visible gives us information, but a standalone, it's not very useful. These ultraviolet and visible spectroscopy need to be combined with other methods in order to give us a complete picture of the structure of a molecule. This is just review. Remember the relationship between wavelength and frequency. Speed of light, wavelength, and frequency. So we know that the units of measure here are meters per second, and the units here are meters, right? That's how long one wavelength is. And this is reciprocal seconds. often called hertz. Now, this is the way we learned it in general chemistry. And we know that since this is a constant, speed of light is a constant, that if one of these goes up, the other goes down. That's an inverse relationship. We're going to modify the use here of frequency by, we're going to base this frequency upon wavelength for infrared spectroscopy, and I'll explain that in just a minute. We also know that as the frequency increases, energy increases. And it increases by Planck's equation. We use Planck's constant times the frequency, and we get the energy of a photon. Or if we only have a wavelength, then we can solve this one for frequency, that's C over lambda, and substitute it in here, so we have hc over lambda would also be equal to energy. And these are SI units. That is, this has to be in meters per second, and energy then would be in joules. And here's a representation of electromagnetic spectrum. Notice as the frequency gets higher toward the left-hand side, your energy also increases up to gamma rays. And gamma rays are the most energetic electromagnetic photons that we know in the universe. In fact, some of them are so energetic that they can approach us from galaxies away. And if the aim is just right, that this gamma ray burst can strip our atmosphere off this planet. Fortunately, though, gamma rays are very directional. It's kind of like sound. You know, if you want to get high frequency sounds from your tweeters, they need to be directional, aimed at the people listening. But woofers, you can put them anywhere. Low frequency is non-directional. So that's analogous to the energy and aim of these waves, these electromagnetic waves. So that's why we don't have to worry too much about gamma rays, because they're so directional. So we see that the visible spectrum, we used to always say is between 400 and 700, but actually it's between 380 and 740 nanometers. These are wavelength numbers. Now, these are not SI units. Nanometers are just more convenient. Remember what a nano is? 10 to the minus ninth, right? So a nanometer is, this would be 380 times 10 to the minus ninth meters. In case you ever had to calculate something here, you'd know how to convert it. We're going to focus on the part of the spectrum that's just to the right in this representation, just to the right of the red. That's why we call it infrared. And then later in the chapter, we're going to look at ultraviolet, which is on the other side, below the purple. And the ultraviolet has much higher, the visible and ultraviolet have much higher energy per photon than the infrared does. And that's important because we understand the concept of resonance. And molecules will not absorb energy unless they properly resonate with something about that molecule. That's why we can use our cell phones inside a building, because the wavelengths travel through the building as if it's not there, you know, unless it has certain characteristics. And then we say the signal is attenuated, which means you don't get many bars on your cell phone. Okay, so how does it work? Well, this model that we see there is typical of spectrophotometers. You have a source, which in this case is the IR laser, producing a certain range of wavelengths. And then you send the beam through a splitter, and part of it goes to a movable mirror, part of it goes to a fixed mirror, and then the movable mirror allows you to adjust for different wavelengths. And they're passed through the sample, and by combining those two signals, we get the presence or absence of an absorbance peak. Now, there are other techniques that are infrared spectroscopy. This is the basic form. There's one that's more commonly used in industry and research now is called the Fourier transform infrared, FTIR. What that does, without going into the mathematics, what that does is allows you to take a snapshot, a couple of things. Take a snapshot of your sample very quickly, and you get all this information in a single burst. And that's very good if you're studying reactions that happen very quickly. The other thing is that it reduces interferences. Remember, interference is like, well, it comes in various forms, but one way is baseline interference. So if you have a lot of noise in your signal, and your signal, say, goes like, the noise is like this, then if you have a measurement where the peak, you expect the peak to be in here, you're not going to see it because the noise is so bad. You have to have a signal that's up here before you can distinguish it from the background. FTIR has lower noise, so it would be something like this. So you could see smaller peaks. Infrared spectroscopy, though, we're looking at anywhere from between 800 to a million nanometers, or 1 millimeter to 800 nanometers to 1 millimeter. So it's a really broad range. Now, we don't see this light, right? It's not visible, right? But we can feel it, right? The warmth you feel on a summer day when you're out on the beach is infrared radiation. What you don't feel is the ultraviolet radiation. You don't feel that till later when your burn develops. But the warmth on site is infrared. We also use infrared to warm our foods. Between the cook finishes cooking, puts the plate up underneath these red lamps. That's infrared radiation to keep your food warm until the waiter or waitress comes to retrieve them. It's the same heat you feel from a campfire. And it's important to recognize, I mentioned this earlier, the energy carried by each photon is greater as the frequency increases. And that limits what the photon can do in a molecule. So infrared photons carry relatively low amounts of energy, and they do not break bonds. They can cause atoms to move and stretch or bend bonds, but they cannot break bonds. There's not enough energy there to break a bond, and that's good. It allows us to gain information about the molecule without destroying it. Now, it's not as important for us here. Percent transmittance is the outcome from this technique. So we have the intensity of the light beam that is detected versus the intensity of the light beam at the source. So what we get is percent transmittance, and the more that is detected, the higher the transmittance. So if the molecule absorbs more of the energy, that means some bond is moving, is stretching or bending, and that's where we're interested in the percent transmittance. So the lower the percent transmittance, the higher the absorbance, and that gives us a key to understanding which bonds are moving. Also, percent transmittance is not a linear response to concentration. Fortunately, we're not interested in that where qualitative analysis is concerned. All we want to know is something about the bonds. So the concentration is constant, and we're interested in just what effect these infrared photons are having upon bond movement, atom movement with certain types of bonds. So that's not a problem. If we were doing quantitative analysis, then rather than percent transmittance, we would use absorbance because it is a linear response, but percent transmittance is not. Okay, so by convention, since we're looking for increased absorbance or decreased transmittance, then our baseline is actually at the top. 100% transmittance means there's no absorbance of the energy. So we sort of invert we look at this upside down. In other words, the peaks are going down. And the more down they go, the more absorbance has occurred. That's one thing that's characteristic of infrared spectra. The other is the expression of frequency. We have been introduced to frequency here as hertz, right, or reciprocal seconds. But for some odd reason, organic chemists have chosen a different unit of measure for frequency. They simply take the wavelength in centimeters and invert it, divide it into one. One divided by the wavelength in centimeters is what they call the wave number. And the way to think of that is a wave number is simply the number of waves that'll fit in 1 centimeter. And stop and think about it. That's not a bad way to go because these are very long wavelengths, right? So it will take just a few hundreds or thousands of wavelengths will fit in a single centimeter. So when you look at these spectra, the higher frequency is toward the left, right? Up to 45, 4750 wave number is higher frequency, and lower frequency is to the right, 5, 400, 300, something like that. All right. You'll also notice that some peaks show a stronger absorption than others. That's self-explanatory, right? The bigger the peak, the stronger the absorption. And these are characteristics that'll help us elucidate the structure of a molecule based upon not just where the peak is located, but its shape, how strong it is, can tell us something about its environment. Okay, these are the types of atomic movements that we see in infrared spectroscopy. There's usually the stretch or the bend, right? And you can get example here is the carbon double bond oxygen, the carbonyl stretch. The distance between the two atoms changes. It gets greater, gets smaller. They just vibrate back and forth like that. And that's the responsible wavelength for that is relatively characteristic of that type of stretch. Or you can get a carbon-hydrogen stretch, and it can be a symmetrical stretch, right? If you have two hydrogens attached to the same carbon, they can both stretch, get longer and shorter together, or they can be asymmetrical. That's on the next page. One can shorten, the other one can get longer, and vice versa. And they go back and forth like that. Then you can get bond bending, where the bond angle changes. And I can't hammer this point enough. Infrared radiation carries only enough energy to cause or respond to these movements of atoms, not enough to break bonds. There's our asymmetrical stretch. And out of plane bending is also possible. Right? So if you get this molecule where you have, that looks like formaldehyde. And it's normally planar, like trigonal planar is what we would say with VSEPR models. But if we apply the correct wavelength of energy, excuse me, the correct wave number of energy, then you can get it to kind of flip-flop like an umbrella. Now, what we see here is each of these types of vibrations has only certain amounts of energy are allowed. So think back to electronic structure. When we talk about how do electrons move in an atom? Well, they move in quanta. They're quantized energy. In other words, it takes a certain exact amount of energy to move an electron from one energy level to the other, or if it moves from a higher to a lower, it'll give up a certain amount of energy, and nothing in between. And that's what happens here also. An infrared photon strikes a molecule and imparts that energy to one of the bonds, one of the atom bond combination, so that they can do something. In this case, we're saying they stretch. So if that is exactly the right amount of energy, then the stretch will occur and the energy will be absorbed. If it's not the right energy photon, then that photon will not be absorbed. It'll pass right through the molecule, no absorption, 100% transmittance. So if we have in this case, our example here is a stretch. If the stretch occurs in such a way that it needs more energy, then we step it up. And we need an infrared photon with higher energy to cause the next one to happen. So these various photons of different energy levels are captured depending on what bonds are in the molecule. And they're very specific. All right. So the nice thing about infrared spectroscopy is with small variations, the types of vibrations that are caused don't change much from one molecule to the other. They might be within a very narrow range of wave numbers, but they're typical. You can find, say this, I have two examples here, 2961 and 1717 reciprocal centimeters. You could find those in a number of different molecules of different structures, but they're like anything above 1500 is relatively consistent across different molecules. That's what I'm trying to say. We'll introduce another topic here in a slide or two. Below 1500, the spectrum gets very complex. And these wavelengths are more unique for each molecule. It's called the fingerprint region. So we typically start with above 1500 reciprocal centimeters and pick out major features. And then we use the fingerprint region as a tiebreaker. All right, there's what I was trying to say. One of the greatest advantages to infrared spectroscopy is that the frequency of a particular type of vibration doesn't change dramatically from one molecule to another. So here we have our examples. We have a ketone on the top and we have an aldehyde on the bottom, and we're looking for the part of the spectrum that identifies that carbon-oxygen double bond stretch. And it occurs in the region of 1720 or so reciprocal centimeters for both of them. Only slight differences there. And this, just like mass spectroscopy, this is a detective story. We're piecing together parts, and we'll use several different techniques to eventually determine what the molecule is. Mass spectroscopy gives us a lot of information, but we might need infrared or UV vis or even nuclear magnetic resonance to complete the story, to nail down the molecule. And it may seem like it's a lot of trouble, but if you were an organic chemist in the old days, you'd be very thankful for these new methods. Okay, so this table and the one on the next page give us general information for identifying the various types of frequencies that are absorbed with the bonds that are being identified at these frequencies. So we'll notice the largest one here has to do with the OH stretch, alcohols, and carboxylic acids. They occur above, well, alcohols are in the neighborhood of 3,000. Above 3,200. And these will be available. I think I put them in one of the handouts. That last handout over there on the right should have these tables in it. These are frequencies. These are stretch frequencies. Most of the stretch frequencies occur in that region above 1,500 reciprocal centimeters. And the bending modes occur in the fingerprint region. In other words, below 1,500. All right, so we've got several bonds identified here, A through E. And we're going to estimate the frequencies for each one of these. All right, so we've got A as an alkene. We should see a peak between 1620 and 1680. Another alkene, that's a carbon-carbon alkene stretch. Carbon-hydrogen of an alkene occurs around 3,000. So it's just below the alcohol. Esters, carbon-oxygen esters, has its characteristic wavelength. The D is another ester, but it's a single bond carbon-oxygen. Remember, an ester has a carbonyl, plus it has a single bond carbon-oxygen. And alkanes. So that looks like the first page of that handout I gave you. We're going to see any single bond stretching with hydrogen occurs in the region above 2,500. A triple bond stretch will occur between 2,000 and 2,500. Double bond between 1,500 and 2,000. Single bond, you're getting into the fingerprint region here and bending modes. So that's one of the reasons that this region gets so complicated, because you're overlapping stretching and bending modes. Okay, now think about, let's see, I don't know if how many people have actually played with slinkies. Remember the slinky? Yeah, slinky. Okay, it's a spring, and but it doesn't have anything on the end of it. It's just a spring that you can do certain things with. But you notice that uh, if you've had a physics course, your instructor probably had a spring that could be, you could change the masses on the end of the spring. And if you hang that spring and you have a mass on it and you stretch it and turn it loose, it'll bounce with a characteristic frequency. Right? If you decrease the mass that's on the end of it, the frequency will increase. Or if you increase the mass, it'll bounce at a lower frequency. And that's the kind of thing that we're dealing with here when we have, we're stretching. We have two factors that are being considered with a stretch. Let's see. Well, here we have only something with hydrogen. Okay, so if we have two things to consider. One is the mass of X and the strength of the bond. Will influence the frequency of the vibration. So if we have something like carbon hydrogen versus nitrogen hydrogen, carbon is a lighter, let's see, nitrogen. Okay, we've got overlapping problems here. I guess, what, did Galen drop out and come back? Must have.
Yeah, my internet's being stupid.
Oh, okay. If we were only considering the masses of carbon versus nitrogen, carbon is a lighter element than hydrogen, so it should have a higher frequency. But notice that it has a lower frequency. So we're also introducing the effect of the bond strength. All right, so if the bond strength is higher between nitrogen and hydrogen, then the frequency will increase. There's a difference between alkenes, alkanes, alkenes, and alkynes. And I think this is predominantly due to bond strength. So the bond strength of of a carbon hydrogen in an alkyne is much higher than it is with an alkene or an alkane. So the frequency increases. And that's based primarily upon the hybridization of the carbon. The alkyne carbon is sp hybridized. It has more s character, which brings the electron density closer to the carbon atom and draws the hydrogen in, makes that a stronger bond. So you can rationalize the difference in frequencies there based upon bond strength. And here's just the author's idea of a difference versus mass versus stiffness of the spring. And the stiffness of the spring is analogous to bond energy. Okay. Oh, that reminds me. There was a question on the last exam that introduced hydrogenation, catalytic hydrogenation of a double bond, and the hydrogens could be added on one side or the other of the double bond. But already there were two deuteriums. Remember the Ds? Okay, we didn't talk about that in class. So if you guessed right, fine. If you didn't guess right, you got credit anyway. Okay, back to this slide. Deuterium, everybody knows what deuterium is, right? It's hydrogen, but instead of just one proton, it also has a neutron, right? It still has only one electron out here. So that makes deuterium a heavier atom. That means if deuterium is attached to some carbon or some oxygen, it's going to stretch at a higher frequency because the mass of the atom is higher. No, excuse me. I got that flipped around. The mass is greater, which makes the frequency slower. Yeah. So, let's see. I can't even read this because everything's in the way. Can't get it out of my way. Maybe I can move it. How about that? Okay. So deuterium is roughly twice the mass of hydrogen because protons and neutrons are roughly the same mass. But the two have nearly identical chemical properties. So a carbon-hydrogen bond has essentially the same strength as a carbon-deuterium bond. So since they are the same strength, our comparison can be limited to the mass of deuterium versus hydrogen. That way we can separate out the effect of mass versus bond strength. So the question is, which vibrational mode, carbon hydrogen strength or carbon deuterium strength, absorbs at a higher frequency in the infrared? All right. So if we find that the ball, using the ball and string model, if carbon hydrogen or carbon deuterium bonds are essentially the same in strength, each one's spring stiffness doesn't change. That means the masses are responsible. So a larger mass will be a lower frequency. So we should have a lower frequency for carbon deuterium versus the carbon, let's see, deuterium, tritium, protium. That's it. Normal hydrogen, one proton is protium. This is deuterium. Add another hydrogen, you've got tritium. So, yeah, we agree on that. All right. So, has anybody heard of Hooke's law? You probably wouldn't have if you didn't have physics or a physical science class. Heard of Hooke's law? This is a more complicated version. The version of Hooke's law that you're probably introduced to first is where the length of the string stretch is proportional to the mass. So if you double the mass on a spring, then the length of the spring is going to be doubled within a certain region. This is a little more complicated, and this has to do with not just the statics of string stretching, but the dynamics, the frequency of the movement of a spring with a mass on it. And the frequency can be calculated with this force constant, which is K. I guess in honor of Hooke, K, they drew K out of his name. And the reduced mass, which is mass 1 times mass 2 divided by mass 1 plus mass 2. And take the square root of that. So what that tells us is that while the K is referred to as the spring stiffness, or in our case, the bond strength, then the frequency is going to increase as the bond strength increases. Okay, so single bonds are going to vibrate with a lower frequency than double bonds and a lower frequency than triple bonds. And with the reduced mass calculated in the denominator, that you're going to have an inverse relationship. So when if only one of those masses increases while the other remains the same, the reduced mass also increases. And if we increase the reduced mass, then the vibrational frequency will increase when the masses are lighter. All right. So I've already mentioned this. It bears repeating. In quantum mechanics, we remember that the absorption of a photon in an atom is based upon its resonance with, or its the quantum of energy required to move an electron from one energy level to the next. And we can also apply that idea to these vibrational frequencies. They occur only if the photon has the correct energy. Now we can get dipole oscillations also. These are stretches that occur with polar bonds. And the polarity of the bond also influences the frequency of absorption for the stretch, or, well, in this case, stretch, but, and that's primarily the one we're interested in here, because stretching weakens and strengthens the bond like that. Whereas bending just kind of, I don't know, for lack of a better term, it flops around. So these stretches tend to be more pronounced with polar bonds than with non-polar bonds. That tells me that we're going to get, with polar bonds, you're going to get a very strong infrared absorption. So if we detect a peak at a given frequency, that means that energy photon has been absorbed. But if the bond is highly polar, we're not just going to get a peak at that place, we're going to get a huge peak for highly polar bonds, like the OH stretch is going to give us a very strong infrared absorption. Whereas with nonpolar bonds, such as the like carbon-carbon double bond, they tend to have a weak, or even sometimes a non-existent IR absorption if the two portions connected to the bond are similar. So what does that mean? That means if we have a carbon-carbon double bond here, and we have a chain here that's like that, and we're going to restrict our discussion to a single double bond and aliphatic chains on either side. Say we have one like that on this side. Let's make it longer. This is going to give you a much stronger absorption than if you have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make it 12. So now if we put that double bond, 1, 2, 3, 4, 5, and then 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a symmetrical bond, a symmetrical molecule around that carbon-carbon double bond. This is going to give a weak or non-existent absorption peak because of the symmetry. And the difference between the two around that carbon-carbon double bond, the more dissimilar they are, the stronger the absorption. So here's an example. Say we have, let's see, I think I have some animation flying in here. Here we go. So if we have this IR spectrum compared HEP1-ene versus HEP4-ene, 1, 2, 3, HEP3-ene, excuse me. We compare these two, then we get a completely, we get the potential for absorbance at 1643 reciprocal centimeters. But for HEP1-ene, you get a very strong peak because of asymmetry. Whereas the HEP3-ene, since one side is 3 carbons, the other side is 4 carbons, you get a very weak peak. Okay. That's an understatement. When you first encounter an IR spectrum of an unknown molecule, it may be daunting. Just pull your hair out time. So one of the subsequent slides is going to give us a kind of a roadmap or a way to approach infrared spectra that should decrease wasted time and effort and anxiety when encountering these things. I remember in one taking an organic course, and lectures and lab were separate courses. So I took a lab. I only had time to do it one night a week, so I took this course in an organic lab that was 5 hours long. So we had 1 hour of introductory lecture to begin with, and then 4 hours in the lab. So I went in I got there at 5 o'clock, and I left at 10 o'clock, and the doors were locked. Right, once you go out of the building, you can't get back in. So one of the projects we had was to identify an unknown material, and we did other things like fractional distillation that we've done in this class with some limited success. But this material that they gave me in this little bottle, it must have been there for ages because it wasn't a pure liquid, right? Or even a diluted liquid. It had a solid in the bottom of it. And so we were supposed to go through and do these various physical and chemical characterizations, including infrared spectra. And so I had a particularly useful lab assistant and suggested that I do an infrared spectrum on the liquid and then isolate that solid material in the bottom. Right, so I filtered it out and put it in this, what we call a new-Joel mold. So solids in the infrared spectroscopy, they have to be ground up with usually potassium chloride is good matrix because it doesn't absorb in the infrared. And then you press it into this thin sheet and put it in your infrared spectrum, and the thinner the better because the light has to travel through it. So I did that, and it came out confirming that the liquid was an aldehyde and the solid was a carboxylic acid. So what had happened was the aldehyde had oxidized over time to produce the carboxylic acid. And that way, I among other things, I confirmed that the particular molecule I was dealing with I forget which one it was, but it was definitely an aldehyde. Now, unfortunately, I skipped a couple of steps on the way to identifying the molecule, and the professor didn't like that. To do everything. So I got to see in that class. Okay. Where do we begin? Well, first place you want to start is outside the fingerprint region. Anything less than 1400, and some authors will say 1500, is the fingerprint region. And anything above that, things are a little cleaner. The peaks that you see there are well defined, not as complicated. They're more characteristic of certain types of stretches. So, yeah, I just got a message. Your internet connection is unstable. Imagine that. That never happens in Greenbrier campus, does it? Yeah, they go out every other week. Start there. Start with the peaks above 1400. And recognize the various peaks for unambiguous information. And that's where that handout is useful. Okay, the correct term is uncrowded. This region is uncrowded, making it easy to spot important peaks. And then, if you need to clarify certain what might appear to be discrepancies in that region, then you go to the fingerprint region and look for peaks that should be there. If you're saying that a particular stretch is occurring 100 to the fingerprint region, and you look for a peak that's going to be indicative of that particular stretch that you're identifying in the other region, and it's not there, then you've got to explain why. Right? Is it a condition where that peak disappears, or is it a problem where you've misidentified in the plus 1400 reciprocal centimeter region? So here's a good example, and this is usually where we start, is the OH stretch, because it makes such a beautiful, large, easily identifiable peak. This broad hydroxyl stretch occurring around 3300 wave number. And then it could be modified, right? If we have that OH in that region, but now we've coupled it with a carbon that's attached to a carbonyl, look what it does to the peak. It doesn't just broaden it out, it adds, it superimposes peaks on that one. So it's not a pure hydroxyl here, not like this cyclohexanol. This dimethylbutanoic acid then modifies that, and there are reasons for that. The reasons for this broad peak plus the modifications of the carbonyl. I think we're going to get that. Oh, my animation should show some of that. This is one of the easiest peaks to identify. If you don't have that peak there, or you don't have the other, you don't have a carboxylic acid or an alcohol. And you can eliminate that from your investigation. All right. Now, why is it such a broad peak? In a nutshell, hydrogen bonding. All right, when you have oxygen and hydrogen, they can hydrogen bond with neighbor molecules and modify the stretch so that it has a very complex association with other hydrogens and other oxygens, and that broadens the band. Carboxylic acids produce these dimers. And there's an example of that down there in the lower left-hand corner. Okay, so the hydrogen bonding allows a rapid exchange of hydrogen atoms from one OH group to another. So we're actually doing proton transfers. What this does is it gives you a whole range of OH bond strengths, and that broadens the peak. Okay, so when you introduce that carbonyl group, and now you've got a carboxylic acid, we produce this dimerization. In other words, you've got two carboxylic acids that can come together with their hydrogen bonding. And this generally lowers the frequency and makes actually increases the potential for hydrogen bonding than you normally would see with alcohols. Okay. You can also detect the presence of impurities. So for this 2,5-dimethyl tetrahydrofuran, we find a weak OH peak there, where we would normally expect to find an OH stretch. This could come from water, it could come from alcohol. If we find anything in that region, and for our purposes here, we've got an internal ether, so we should not see anything in that region for the alcohols. But if we see anything there, then it's possible that we have a contamination problem. Let's see. If the compound itself had an OH group, the peak would be much, much more intense. All right. So it just emphasizes the point. Get rid of your solvents before you do an IR spectrum. Okay, we've been talking about carbon, hydrogen, and oxygen hydrogen stretches. Nitrogen hydrogen stretches, what are they? How are they different? Well, first of all, they're similar, but there are noticeable differences between the two. First of all, oxygen is more electronegative, so the bond strength is going to be higher, and the hydrogen bonding is going to be more intense than with nitrogen and hydrogen containing molecules. So we see a little bit higher frequency. I think because the nitrogen is a heavier atom, the bond strength is different, but the nitrogen is a heavier atom, so we're going to have higher frequencies, which means more energy. Hydrogen bonding still exists, so the band is going to be a little broad, but not quite as broad as the oxygen-hydrogen band. All right, what are some noticeable differences between the two? Well, the intensity of the nitrogen-hydrogen stretching band is usually less than that of the oxygen-hydrogen stretching band. And think back to a couple of slides before. The intensity is dependent upon the polarity of the bond. And so nitrogen is not as polar as oxygen, the polarity of the nitrogen-hydrogen bond is going to be less also, which means the intensity is going to be less than the oxygen-hydrogen stretch. And it's not as broad because the hydrogen bonding is not as intense for NH as it is for OH. Okay, so you can also, you'll see possible multiple peaks where nitrogen hydrogen is concerned. And that has to do with whether it's a primary, secondary, or tertiary amine or amide for that matter. So that first example where we have the amide with a nitrogen and two hydrogens, you're going to get two separate peaks there. Whereas if you only have if you have an one hydrogen attached to the nitrogen and a carbon group of some kind on the other end, then this secondary nitrogen is only give you one peak, and it's going to be at a lower frequency also. And if you know your molecule has nitrogen in it, and you suspect that there's an amide involved or an amine involved, and it turns out to be a tertiary amine, you will not see a nitrogen-hydrogen peak because there are no hydrogens there. Okay, so this is an attempt to explain why you get the double peaks and the single peaks. When you have two NH, two hydrogens attached to that nitrogen, you have two possibilities for the stretch. You have a symmetrical stretch and an asymmetrical stretch. So you get two different peaks. One occurs at higher energy than the other. Okay. That didn't take much explaining. Let me flip my hard copy just so I get my bearings. How far along are we? About halfway. Okay. This carbonyl group, the carbon double bond oxygen, is found in many classes of compounds. That includes ketones and aldehydes. We're familiar with those. Carboxylic acids have them. Esters have them. Amides have them. Typically, the carbonyl stretching absorption is quite strong and the band is relatively narrow, usually making it easier to spot. So this is going to be a stronger bond, and the carbonyl stretch should be at a higher frequency than the CO or the OH stretch. That's what I'm expecting. Of course, I could be wrong. In fact, I am. We're going to have an explanation for why that is. So what we do see, though, is for each of these classes, we find that the CO stretch is, and that's probably because the carbon and oxygen are more massive than the hydrogen. Right, so it's going to vibrate at a lower frequency. That's the only thing that makes sense to me. So we notice that the highest frequency is for esters. Aldehydes are less, ketones the next, and amides the lowest frequency. We can explain some of these. The carbonyl by itself will occur in that region, like 1700, 1600. But if we also have the possibility for conjugation, Conjugation will lower the frequency also. Now, how do we, okay, what we're doing is we're stretching the electron density. We're delocalizing electrons from that carbonyl into two other bonds, right? Between the ene and the single bond carbons and the carbonyl. We're removing some electron density that should weaken the bond, and it lowers the energy. We already know that. But by weakening that bond, now we have a lower frequency because the spring is not as tight. In other words, the bond's not as strong, so you get a lower frequency for a conjugated carbonyl. And we can generalize, right? The stiffness of a CO bond is generally increases in the order of amide, ketone, aldehyde, and ester. Decreasing the stiffness with conjugation wherever possible. Okay. We mentioned this earlier, I think. Carbon-carbon stretch for alkenes. Oh, we're going to extend this to aromatics. Okay. So we know that the strength of the signal for a carbon-carbon stretch is increased by asymmetry around that carbon-carbon double bond. Aromatics, on the other hand, are much weaker. We have weakened the bonds further by their aromaticity. We're delocalizing the electron density, which decreases the strength of those carbon-carbon bonds, which also should decrease the frequency where you're going to find them on the IR spectra. Sometimes the carbon-carbon stretch is difficult to identify. For one reason, they tend to occur in the same region as the carbon-oxygen stretches. In which case we can overlap, things can be overlapped, and okay, I'm playing with my video here, and obscure one another. So that's in the sciences, that's called interference. In analytical chemistry, it's called interference. And for symmetricals, the peak starts out at a very low frequency, very low intensity anyway. So sometimes you can't distinguish that one. So this is one of those cases where we need an alternate analytical tool to fill in the blanks. If we suspect that there's a carbon-carbon double bond in there, and we could do that with mass spectroscopy, then and the IR doesn't show it, then that would be one explanation that we have a very symmetrical carbon-carbon double bond. So here's what it looks like for aromatics. The first aromatic molecule shows us carbon-carbon stretches, but okay, we're trying to simplify things here. We call them carbon-carbon double bond stretches, but we know that aromatic compounds don't have carbon-carbon double bonds, but they have something in between because of the delocalization, the spreading out of their electron density around that ring. But I guess for simplification, we're going to call it a carbon-carbon double bond stretch. And they generally have several peaks. And now we're getting very close to this fingerprint region. We're right on the cusp. So that first one shows those 3 peaks. And we get a similar 3 peaks, but for a symmetrical molecule, it decreases the intensity of a couple of those peaks. All right, that wasn't a whole lot of help. Just that's where they are. What about those other peaks? Well, we haven't talked about those yet. So in the 3,000 range. What do we see with alkynes and nitriles? Those are much, much stronger bonds. So they should vibrate at somewhat higher frequencies than the double bonds. And that's typically the case. Carbon-carbons between 2100 and 2260, nitrile bonds between 2210 and 2260. So you could get some overlap with those also. So how do we distinguish between these two groups? Well, we look for the carbon-hydrogen bonds with an alkyne. If we see a peak, say in the 2100, 2260 range, and we want to be sure that it's an alkyne and not a nitrile, then we look for a carbon-hydrogen bond. I suppose you could have a carbon-hydrogen bond if that were hydrogen cyanide, right? But if that carbon on a nitrile is bound to another carbon, then you won't get a triple bonded carbon with a hydrogen. You'll have maybe a neighbor would have the carbon hydrogen. So if you have one sharp peak, that consists that's a terminal alkyne. If that peak is absent, then you have an internal alkyne. That's one way to distinguish the two. And the carbon triple bond carbon stretch in an internal alkyne is weak or maybe even non-existent. Whereas the nitrile stretches are moderately intense. So we're looking for position and intensity to help us to distinguish among the two. All right. So here we've sort of put everything together. Carbon-hydrogen stretches appear between 2700 and 3300. Okay. And they're typically characteristic of certain types of carbon-hydrogen associations. So if the carbon is with an alkyne, then you're going to get the stretch in the 3300 range. If it's an alkene, it's a little less energy. Aromatics, similar. We mentioned that earlier. The alkenes and the aromatics may overlap and obscure one another. Alkanes at a lower frequency as we decrease the strength of the bond. That's what we're doing here. Aldehydes tend to have 2 peaks. And like I said, this is a detective story. If we're looking for something that's not there, then we have to explain why it's not there. And hopefully that will help elucidate the structure of the molecule. Okay, so here we have this aldehyde. We have carbon-hydrogen peaks. In fact, there are 2 carbon-hydrogen peaks here. Now, why would that be? Well, if it was just a simple case of hydrogen bonding, it should just broaden the peak. But two different peaks means that we've got two different types of molecular movements here, atomic movements, maybe a stretch and a bend. So if we have a carbon-oxygen, a carbonyl stretch in the neighborhood of 1720, and there it is right there, you can see it between 1500 and 2000. So that's indication that we have either a ketone or an aldehyde. Then we look for, if we have peaks at 2720 and 2800, it's almost certainly an aldehyde, because that is a carbon-oxygen peak. And if it were a ketone, we wouldn't have that. We're really getting down to the weeds now. And that's where it can get, you can get bleary-eyed. Okay, carbon-hydrogen stretches typically occur between 2800 and 3000. But they're so commonplace in organic molecules that they're not usually important or useful for structures. That's a good analogy. It's like trying to identify a car from its tires. Of course, if you watch some of these shows like, what's the one at New York and one of them's in Miami, where you have the forensics? I forget the name of those TV shows. The New York one had Gary Sinise in it. And let's see, CSI Miami, CSI New York, right? Some of the things they come up with, what, how did you get that out of there? Like they do their DNA testing and like takes 10 minutes. So we can identify this car by its tires only if it's a very, very, very expensive car. Then they have a specific type of tire that they'll only run on, like rated for 120, 130 miles an hour. Okay. The alkane carbon hydrogen stretching band is perhaps most useful when it is low intensity or absent altogether. So looking for the presence of the alkane carbon hydrogen stretch is the wrong approach. We need to look for low intensity or even absence of these stretches under certain circumstances. So, since there's a possibility for very large numbers of carbon hydrogens or very small numbers, depending on the molecular makeup and the index of hydrogen deficiency. Like if we have lots of double bonds, lots of rings, then we're going to have more deficient, and that's going to reduce the number of carbon hydrogen stretches that you can identify. That will also decrease the intensity of the peak. So if you do find a peak that's characteristic of alkane carbon hydrogens, then the number of those carbon hydrogens will be a good indicator as to how substituted the molecule is, or its index of hydrogen deficiency. So here we have 2 ethyl hexane 1-ol, 17 carbon hydrogen bonds. That makes the carbon hydrogen stretching band even more intense because we have all those carbon hydrogens. In fact, even more intense than the oxygen hydrogen. Whereas ethanol only has 5 carbon hydrogens, and that makes the carbon hydrogen stretching lower intensity. Or if we have diphenylmethanone or benzophenone, that's either one is proper, I think. has no carbon-hydrogen bonds, so peaks in that region are absent. All right. Okay, so here's what was promised earlier. A uh, roadmap, so to speak, for using IR spectra. You want to go first to any peaks that are above 1400. They're very, it's a clean region, and they're either there or they're not. If you do find some there, then you go to identify the peaks to tell what types of bonds are present. Look especially for the presence or absence of peaks for OH stretches, NH stretch, carbonyl stretches, double, triple bonds, nitriles, and the carbon-hydrogen stretches, which will be either very intense or low intensity or non-existent, depending on how many carbon hydrogens you have. Yep, let that get in. Need that in my pocket. If you don't have any, okay, that's if you have a single peaks available. If, on the other hand, you have multiple peaks identified, functional groups that have more than one type of bond, then you go, for example, to what do they do to each other? Like the carbonyl and the hydroxyls in carboxylic acid, how do they affect one another? Or the amides, how do they affect one another? So here you have multiple bonds that are influencing the absorption spectrum of the other. And then we go to the next slide. So look for special characteristics of these absorption peaks identified in step 1. For instance, is the OH absorption consistent with an alcohol or a carboxylic acid? Right? Is the NH absorption consistent with NH or NH2? Right? If it's NH2, it's probably a split peak. If it's NH, it has a single peak. If it's a tertiary amine, there won't be any peak for NH in that region. Are we looking at a carboxylic acid or an ester, a ketone or an aldehyde or an amide when you're looking at carbonyls? Does the carbon-carbon double bond absorption suggest an alkene or an aromatic ring? How about the absorption of triple bonds? Right? Are they characteristic of and these are going to overlap. Do you have any in the region of alkynes or nitriles? Is the alkane carbon hydrogen absorption noticeably weak? And what does that suggest? Well, most often it suggests there are very few of them there, if there are any. And then establish whether your carbonyl bond is conjugated. If it's conjugated, it's going to weaken. It's going to weaken the bond and shift its absorbance slightly toward lower frequency. And that will also mean that if you have a carbonyl that is conjugated with an alkene, you should also look for the presence of alkene or aromatics in your spectrum. All right. So here we have an unknown. It looks to me like there's an alcohol in here, right? That we know okay, we're given C7H8O, which is our molecular formula. And I see a hydroxyl stretch there. So that O is probably one of those hydrogens is attached to that O, and the O is attached to a carbon. That's the first thing I noticed. There's no intense band around 1700. Okay. So we're not looking at a carbonyl. Here's something that we've used before and haven't seen in a while: the index of hydrogen deficiency. So we're looking at the number of carbons, right? So we've got how many carbons? 7 carbons. So if this were a completely saturated molecule, it would be 2 times 7 plus 2. Right? 2 times 7 plus 2 equals full saturation. It would be 16. Right? But we have, let's see. Oxygen. We don't have a nitrogen, so it doesn't have any. Let's see. We don't have any halogens. So, right, there's no nitrogens. For each nitrogen, we add one hydrogen and one carbon. Right, but we don't have any nitrogens. Right. So the index of hydrogen deficiency is divided by 2. That's not right. Minus y. What is, oh, the number of hydrogens, excuse me, 8. Minus 8. Forgot that part. 10 divided by 2. So that's 4. Index of hydrogen deficiency is 4. So it could contain up to 4 rings, 4 double bonds, or 2 triple bonds to get that value. Relatively few carbons, so we are strongly considering an aromatic ring. And I would agree with that. Yeah. Because we have relatively few hydrogens. All right, we've already covered this. We've got the OH stretch, an alkene or an aromatic stretch at 3050. Is that there? 3050, yes. All right, so we do have the potential for an alkene or aromatic at 3050. Alkane stretches between 2800 and 3000. 2800 and 3000 are very few and far between. So that's consistent with very few carbon hydrogens. How about 1450 to 1600? Yeah, we got one there. Carbon-carbon double bond stretches. All right. Notice the absorption around 3050. Around 3050, which belongs to an alkene or an aromatic. And the absorption between 1450 and 1600, which belongs to a carbon-carbon double bond stretch. So we're following these steps that were given in the previous slide. So an alkene typically exhibits one peak about above 1620. Whereas an aromatic ring typically exhibits 2 or 3 peaks in the 1450 to 1600. And I see multiple peaks there. It's a split peak. In this case, we appear to have an aromatic ring with an IHD of 4. So we're going to have probably a benzene ring because there's 7 carbons. And alkanes, the intensity is very low, which means very few carbon hydrogens bonds. It's much smaller than the OH band. There are relatively few alkane carbon hydrogen bonds. That's okay. We've identified that. Relatively low number of carbon hydrogen bonds would be consistent with 6 out of the 7 carbons being part of an aromatic ring. So we would take this one and make our aromatic ring first. Right? And we would have probably 5 hydrogens here because we got a carbon that's not part of that ring. The carbon has to come off here. So that's 6, that's 7 carbons. And then we would need to add a hydroxyl and a hydrogen. Let's see, 1, 2, 3, 4, 5, 6, 7 hydrogens, 1 oxygen. That's probably our molecule. Yeah, that's phenol. Okay, these are possibilities. All right. I sort of jumped the gun. We could put the hydroxyl on the molecule by itself, like there's our methyl group, there's the other carbon, and here's the OH. The problem with that is, how about the hydrogens? This is going to have 3 hydrogens on it, right? So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. Go back. Yeah, that would work. Okay. So we need to break the tie somehow. At this stage, we know that the compound has a benzene ring and an OH group. We still need to account for 1 more carbon atom. That's why we propose these 4 different structures. Okay, we're not going to get an answer because now we've run into our roadblock for IR spectroscopy. We can't distinguish among these 4 different molecules. All right. So my guess is that mass spectroscopy could break the tie for us because of the mass charge ratios that would be produced from breaking this molecule apart. We'd get a different spectrum for each one of these. And we get a different spectrum. We could potentially determine whether the alcohol was on a primary carbon rather than attached to the ring. That could break the tie for us. But if it didn't, then we'd be stuck with H, I, and J still. All right, here's another one. All right. All right, we do have a broad peak at around 3,000, but it has some structure to it. It's not smooth like an alcohol would be. All right, what's the basic structure required? Okay. All right, so we're looking at, all right, that's why they're pointing at 1682 and 1617. That gives us the potential for carbon-carbon double bond and carbonyl. Did we do okay, the IHD of 2, IHD of 2, same as the basic structure. So we can't add any double bonds, triple bonds, or rings. All right. I'm not much help with that one. I thought we were going to look at that the peak around 3,000 should give us some information. What if where's our around 3,000? And it could be an alkane. It could be an alkene is probably what it is. Yeah, that's where they got the alkene. And then 1682 and 1617. 1617 also says alkene. We don't have one at 1630, so that's, or 1690. Yeah, it could be, well, amide, it's not going to be an amide because there's no nitrogen in the molecule. Okay, so that's why we're looking at carbonyl. I missed that one. Where's the carbonyl coming from? Carbonyl. Here we go. 1682, 1617. Ketone aldehyde. Very strong peak. Okay. That's why we're saying it's a ketone. That's the only one that fits. And then an IHD of 2. We start off with C8H14. 8 times 2 plus 2 would be 16, 20, minus the number of hydrogens, which is 14. And that's divided by 2, 6. Let's see. Did I do that right? I'm saying 3. They said 2, right? IHD of 2. Oh, I forgot the oxygen. What do we do with the oxygen? Oxygen doesn't have any effect. No. Remember that? Oxygen has no effect on the IHD. Four atoms, 14 hydrogens. Did I do this right? 2 times 8 is 16. Oh, that's 18. Excuse me. Can't even add. So that's 2. Okay, so the IHD is 2. Right, we couldn't add, since we do have the carbonyl and we have the carbon-carbon double bond, then we can't add any double bonds, triple bonds, or rings to the structure. So the rest of the carbons have to be added around the molecule, right? Either in branched or linear fashion. All right, what are we looking at here? This has nitrogen and oxygen. So nitrogen is going to subtract and add, is going to add to the IHD for each nitrogen. Put the formula up here so I don't have to keep flipping back. C7H, what, 13? So we have 7 times 2 plus 2, 16. And nitrogen subtracts 1, I believe. No, nitrogen adds 1, plus 1. And the oxygen doesn't do anything. Divided by 2. So this is 14, 15, 16, 17. Divided by, oh, I forgot to subtract the hydrogens. Excuse me. So plus 1. And then minus the 13 hydrogens. Okay. So this is 14, 16, 17, 4. So that's equal to 2. It's an IHD of 2. And then we're looking for peaks. And they're stretching me too far. I'm no master at IR, that's for sure. So let's see, coming up on 11. All right. So how did they get the carbon triple nitrogen, the carbonyl, not carbonyl, nitrile. Nitrile. So let's look at the nitrile would occur at 2210, 2260. 22, let's see, this is 20. There it is right there. That peak, that right there. That's the nitrile stretch. Okay. That's where the nitrile comes from. And let's see, we've got one at 2900, 2800. Aldehyde, possible aldehyde. Ooh, ether. How'd they get ether out of that? Oh, we got an oxygen in there. We don't have an OH stretch anywhere. And that's not really. If we had an aldehyde, there should be a 1680 to 1750. And there's not. Okay, so it can't be an aldehyde. All right, that's why that's why that oxygen is converted into an ether, because there's no evidence for a carbonyl in there anywhere. That oxygen has to be an ether. All right, so those are proposed structures, and that's about as far as you can go with it. As long as the IHD comes out characteristic for those molecules. Okay, bending vibrations. We looked at this earlier. See what they have to say about it. Okay, we're in the fingerprint region, which tends to be crowded with a large number of peaks. That's an understatement. Therefore, we generally don't turn our attention to bending vibrations unless we expect a specific type of absorption to be present. This this is where I don't know if you call it artificial intelligence, but expert systems might come in, where you go to the fingerprint region and you let it read the peaks and put those into your database. And then it's kind of like going into a black box. And these peaks go into your black box, and the library that you have installed in your computer tells you that this arrangement of peaks should give you these different molecules. And those molecules, then you could use those with the information you gained from the plus 1500 region to pick out the right one. I think that's probably how it would go. All right, so let's see. Suppose we have this monosubstituted benzene ring, excuse me, benzene ring, and we're going to see these two peaks at 730 and 759. secondary butylbenzene, which represents the bending modes of a monosubstituted benzene. So this is we're looking at fingerprints. So if we see these two peaks together, 730 and 759, and we already know that we have a substituted benzene ring, then that's going to tell us that this is a monosubstituted benzene. I wonder if that could help us with our previous molecule. Let's see, what was that? 730, 759. Go back. No. Possibly. Let's look at the spectrum. Let's see, there's 750, 730. Yeah, it's a little iffy. I don't know if that would help us. Okay, back to where we were. Here we go. Whereas the para-disubstituted one has a peak at 833. And the 730, 759 are absent. So this is just one example of the fingerprint region helping us to distinguish between these two. Now, do they have the same? Let's see if they have the same number of carbons. 6, 7, 8, 9, 10, 6, 7, 8. No, they have different numbers of carbons. Right. So we're not making a direct comparison there. We're just saying that the para-disubstituted has this peak and the monosubstituted doesn't. They have different fingerprint peaks. All right. All right, so much for IR. So let's take a look at ultraviolet and visible. UV vis, we often call it. So we're looking at a similar outcome, only with UV vis. UV vis is more often used in quantitative analysis, like we did with, well, since I didn't have you in my class, we used with our chemical kinetics experiment. We had a colored molecule like blue #1 dye, and we hit it with bleach, and we watched its progress with a decreasing absorbance. And we wanted a linear expression of concentration, so we used absorbance, not transmittance. So if we take transmittance, divide it by 100, and take the negative log of it, we get absorbance. And the reason we use absorbance is simply because it is a linear response to concentration. It incorporates the log function into the values, so it straightens out the curve. But you essentially obtain the spectrum the same way you do with any other electromagnetic spectral analysis. You have to have a way to select the wavelengths, and then you pass them through your sample and you measure the intensity before and the intensity after. And that ratios, and all of this happens internally with your spectrometer. So if you're going to set it on absorbance, it'll automatically take the negative log of the ratio. Now, if we're only interested in the wavelength where these peaks occur, then absorbance is as good as percent transmittance would be as good. But the way we present the data is absorbance is a positive peak rather than a negative peak. because we took the negative log. So that inverted the peak. So that it looks normal now with the peak going up rather than the peak going down. All right. And we're talking about the visible region, what, 380 to 740, was it? And then anything less than 380 is ultraviolet. Down to in the neighborhood of about 120 to 150 nanometers. And that gets to be a problem. When you get down that low, the air that's in your system absorbs energy at that wavelength, at those low wavelengths, short wavelengths. So if you're going to go down in that region, you probably have to, and the primary culprit is oxygen. Oxygen is a strong absorber in that region. So what we used to do when we needed to look at that lower wavelength region was flush the system with nitrogen. It drives all the oxygen out of it. Okay. Buta-13-diene has an absorbance peak at 217 nanometers. And just a single peak. All right, what does that say about the molecule? Well, the whole point of this chapter, well, these several chapters, is to relate the spectra to the structure, right? And we can say something about the structure of this molecule. Now, if we know buta-13-diene is the name, then we know the structure already. But if we were just to look at that spectrum and say, all right, what does that mean? Then we would need some sort of guide to tell us that 217 was specific for a particular type of structure. And here we have a conjugated double bond system. And what conjugated systems do is they shift the absorbance wavelength to longer and longer wavelengths. All right, so if we had, let's see, if we had a non-conjugated system, you know, that wouldn't work for this molecule because it's only got 4 carbons. If we had 6 carbons and we had a conjugated a double bond system versus a non-conjugated, then we would see that peak shifted for the non-conjugated one into shorter wavelengths. All right, we're still in the ultraviolet here. Now, most molecules will have a more complicated spectrum than this. This one simply has one peak, and the molecule was chosen for that factor. But even if you have multiple peaks, one of them is going to be the strongest absorber. The relative absorbance will be highest for one of those peaks, and that we call the lambda max, the wavelength of maximum absorbance, excuse me. And when we're trying to quantify these molecules, if we want to know the concentration of a particular molecule, then we would pick the lambda max because it has a stronger absorbance, and the lower the concentration, the lower the absorbance, and that broadens the range at which we can detect it. The only reason we would go to an alternate wavelength is if there was a mixture and one of the molecules also absorbed at our lambda max. We could find another wavelength where the offending molecule did not absorb, then we would go to that one. But typically we go to the lambda max if we're going to quantify, if we're trying to determine concentrations of a given species or a molecule. Sometimes we call them chromophores, which just means they're colored parts of the molecule. Okay. Unlike infrared photons, which increase a molecule's vibrational energy when they are absorbed, the energy of UV visible photon is taken up by one of the molecule's electrons. So now we're into a different mode of absorbance. The absorption of energy now is not by vibration, but by electron movement. So at this point, we probably want to consider molecular orbital theory, because that gives us a continuous band of energy levels in which we can insert electrons at different energies, and then we can excite them with absorbed photons of light. All right, here's some examples. Alkanes and cycloalkanes are usually less than 150 nanometers. Ethenes around 161. Let's see. Hex 1e. Okay, we're working increasing lambda max. So we've got hex 1e, penta 1,4-diene. So now we have a non-conjugated system at 178. And if we had that same molecule, look just to the right of that penta 1,4-diene to trans penta 1,3-diene. There we have a conjugated system, and notice the difference in the lambdas. For the one on the left, 178, and the one on the right is 223.5. So when you conjugate a system of double bonds, you increase the wavelength of absorption. Cyclohexene 182 versus nothing. No comparison there. Hex 1-ine, we're increasing absorbance. And then as we conjugate bonds, we increase their absorbance. And that's in the middle column. And on the So we're working our way through more and more conjugation, it looks like, until we get to formaldehyde over in the middle of the far right column at 280, at 280 nanometers. We're still in the ultraviolet. But if we get enough conjugation, say for beta carotene or for astaxanthin, which I worked with in my master's thesis, and it's very large numbers of conjugated double bonds. Now we're getting into the visible range. So that's why beta carotene is orange and astaxanthin is red. We've conjugated those bonds to the extent that now we're into the visible range. And remember, when we perceive color, we perceive it in two different ways. One is light strikes the molecule, and if we're on the other side of the light source, we see what's not absorbed. If we're on the same side as the light source, we see what's reflected. So this 455 nanometer absorbance max, lambda max, means that it absorbs that wavelength. And what we see is what's left over. That's why beta carotene is orange. Roy G. Bibb, red, orange, yellow, green, blue, indigo, violet. So it absorbs in the blue end of the spectrum, and we see what's left over, which is orange. Okay. So molecules that contain only sigma bonds don't absorb in the UV or visible region. Their longest wavelength is too short. So they're way out of the UV invisible region. Now you're working into the X-ray. Right? So they will absorb in the X-ray, but the risk you run with irradiating a molecule with X-ray or gamma ray is that it could tear the molecule apart. So you have to be careful with your intensity. Molecules that have at least one pi bond have their lambda max at around 160. And as I said before, the value of that lambda max increases as the extent of conjugation increases. Now, the lambda max tends to be much greater for species that have lone pair of electrons than those species that have no lone pairs. So if you introduce, say, an oxygen or a nitrogen, nitrogen having one lone pair, oxygen having two lone pairs, then you start shifting that wavelength into longer and longer wavelengths with those lone pairs. All right, so how about this one? Rank these species in order of lambda max for their longest wavelength absorption. All right, so what do we have? All right, for something like this, I would, well, rather than draw the molecules, I'm going to refer to this and say the longest wavelength from what? In order of their longest wavelength, so from shortest to longest. The longest wavelength is going to be V. That's conjugated. Plus, it's got a lone pair. So V, right? V has wavelength, the longest wavelength for two reasons: conjugation and lone pair. S is not conjugated, but it does have a lone pair. So I would say S would come next. Then how about the shortest one? That would be U, right? U only has single bonds, sigma bonds. Right? What does that leave? Well, T, right? T is the only one left. So I would say UTSV. Let's see if I'm right. Or at least not that I'm right, that I agree. Molecules S, T, and V have pi bonds where U has only sigma bonds. Therefore, the longest wavelength absorption will be the shortest for U. Okay, we got that one right. That's over here. Molecules S and V have lone pairs on nitrogen, whereas T has no lone pairs. Therefore, the longest wavelength absorption, T will be shorter than the ones for S and V. So T is here. Yep. And then we have to decide which comes first, S or V. And then since V is conjugated and S is not conjugated, V should be the longest wavelength there. Well, that's pretty simple. All right. White light is a mixture of colors. Okay, now we're estimating between 400 and 700. So when a compound absorbs a particular visible wavelength, their eyes detect the absence of that wavelength as a characteristic color. All right, I already said that. These slides need to keep up with me. Liquid formaldehyde is colorless. It absorbs at 280, which is in the UV region. Therefore, all the colors of white light pass through formaldehyde, reach your eyes, so the white light appears unaffected. That makes sense? All right. Our carrots are another example where we have beta carotene. It absorbs at 455. So out of white light, it will absorb the blue end of the spectrum and leave behind the orange. So here we have, I don't know if you've seen this before, this color wheel. this is okay. This color wheel is ranged to give us complementary colors. So if we look at this wheel and we see beta carotene absorbs blue, 455. The complementary to blue is right across from it on the other side, which is orange. So that's why we see orange from carrots. Let's see. Moving into the more green or blue-green, which is where my astaxanthin would occur, then its complementary is red. Right? So that's why crawfish and lobsters are red, because the astaxanthin in their carapace absorbs in the green region. These are complementary colors. All right. I'm sure you've been introduced to this before, the Beer-Lambert law. It just says that when you measure absorbance of any solution or any molecule, there are three factors that have to be considered for the intensity of that value, that absorbance. One is, I used to write it like this. It's easier to remember: A, B, and C. C is concentration, right? If that changes, increased concentration, increased absorbance. B is path length. I think they have L here. And A is the absorptivity of the molecule. So each molecule is different. Some molecules have higher absorptivity than others. But if you're just considering concentration as your guide, then as you increase the concentration, the absorbance will increase. And what you do is your cell is a fixed path length, and you're only looking at the same molecule each time. So these are constants. And the only value that varies is the concentration. Molar absorptivity, that little E. It's intrinsic to the molecule. All right, so I've already said that. Typically, your path length in a UV vis spectrometer is 1 centimeter. I see these little square cuvettes. They're 1 centimeter path length. You can get them with smaller or larger path lengths. I used to use a device that analyzed for carbon, hydrogen, and nitrogen in organic samples. And one of the pathways that the combustion products went through was an infrared cell that used Beer-Lambert law. And the cell had to be that long to give you enough absorbance to detect it. Now, that instrument was a pain in the ass. It was always breaking down. It worked. Eventually, I replaced it with one that worked better. Okay. Oh, by the way, it was made by a company out of not Detroit. No, not Detroit. The other side, St. Joseph, Michigan. And the company was called LECO, appropriately named, because that thing was leaking all the time. Okay, UV visible spectroscopy and quantitative measurements. All right. Absorbance is linear up to a point. If you surpass that point of linearity, then you might as well stop. You dilute your sample. That's the only option you have. So if we want to track the progress of a chemical reaction, say we're going to make an alkene out of this halogenated benzene, then we can follow the progress of the reaction, because the molecule on the left doesn't absorb at that wavelength. So we set up our lambda max to absorb at 244 for our molecule, and we can watch the progress of the reaction. And this is kind of what we did with that we do in my second semester general chemistry class when we are talking about kinetics. We follow the progress of the bleaching of the blue dye using lambda max for the blue dye. And we can watch the absorbance decrease as the bleaching process proceeds. Okay, in this case, we're trying to find out if this elimination reaction occurs as an E2 or an E1 mechanism. So because the absorbance is directly proportional to the concentration, the initial reaction rate is simply the change in absorbance divided by time. And if the concentration of the base, the sodium alkoxide, is doubled in the absorbance that is measured over that initial period is doubled, we can conclude that the reaction proceeds by the E2 mechanism, not the E1. The E1, remember the E1, the chloride would have to leave first and make a carbocation in order for it to be an E1. But since the reaction is dependent upon the concentration of the base, we know that it's an E2. All right. We mentioned this earlier. We're looking at, in fact, I inferred that we should be looking at molecular orbital model here because of the effect of conjugation. We need to look at this in terms of not an atomic orbital situation, but as a molecular orbital, because those electrons can be delocalized. So the longest wavelength corresponds to the transition of an electron from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. In other words, the shortest energy jump. Right? A long energy jump means lots of energy, which means shorter wavelength. The shortest wavelength, the shortest energy jump is going to give you the longest wavelength, the lowest energy. So if the energy jump is from the HOMO to the LUMO, then that should give you the longest wavelength. So this is an attempt to try to explain why that happens. When you have all sigma bonds, the jump between the HOMO and the LUMO is huge, which makes the energy jump even outside the range of ultraviolet. You're getting into X-rays there. But when you have a double bond, the HOMO and the LUMO are close together. The pi and the pi star are much closer together. The sigma and the sigma star are usually very far apart. Right? The pi and the pi star are closer together. And then we looked at earlier, when we looked at conjugation, we saw that the pi 1 and pi 2 were on the lower energy side, and the pi stars are on the higher energy side, but you do get a closer gap between the pi 2 and the pi 3 star. And the more conjugation you get, the closer the HOMO and the LUMO get. So this is an attempt to explain why multiple conjugations increase the wavelength, decrease the energy of the jump. And that I already said that. Now, what about lone pair of electrons? Well, where do the lone pair of electrons reside? They're in non-bonding molecular orbitals. That makes them higher in energy than the molecular orbitals, the bonding molecular orbitals. The bonding molecular orbitals are low. Non-bonding are the same as the atomic orbitals that go in. So that's where the lone pairs reside. And then the LUMO is a star bond. So there's a shorter distance between the HOMO when it's occupied by lone pairs. Right? So lone pairs, this is an attempt to explain why lone pairs tend to give you a longer wavelength, absorption wavelength. And that's it, all she wrote.